Hello everyone, this is Professor Roman, and this is the second lecture in the course on ring theory. In the first lecture I introduced the course, so now we're ready to get started with rings. And of course there's no better place to start than with the definition. Informally speaking, a ring is an additive group, meaning it's an abelian group under addition, together with a second, weaker binary operation called multiplication. And it's weaker in the sense that although multiplication must be associative and must have an identity element, and I'll have more to say about that in a few minutes, not all elements need to have multiplicative inverses. And this has a profound effect on the behavior of multiplication, as we will see in some upcoming examples. Here's the formal definition of a ring. A ring is a non-empty set R called the underlying set or carrier set for the ring, together with two binary operations, addition and multiplication. This is a list of the properties required for R to be an abelian group under addition. Multiplication must be associative. There must be a multiplicative identity, which we denote by 1. And to connect the two operations, there are distributive laws. A right distributive law and a left distributive law. A ring is said to be a commutative ring if multiplication is commutative. One doesn't use the term abelian for rings. A group can be a commutative group or an abelian group, but for rings we just use the term commutative. We don't use the term abelian. The identity element of a ring is unique, and that's just a simple one-line proof which you should supply yourself before looking at this. It's the same proof we gave for group uniqueness of identity in groups. It's important to mention, however, that many books on ring theory do not require that a ring have a multiplicative identity. These, I think, tend to be more advanced books. So we must make a distinction between rings with identity and rings with or without identity. And those are often just referred to as rings without identity. What that means is they might have an identity, they might not. It's not required by the definition. But for us, the term ring will mean ring with identity, although on occasion we'll talk about rings without identity as well, just for contrast. I'm sure it's not a surprise that when rings with identity have better behavior than rings without identity. It does make life simpler when there's an identity. And I think that's why most introductory books on ring theory require a multiplicative identity. There is a price to pay, however. Just as an example, the set E of even integers would be a ring if it were not for the identity requirement. In other words, it's a ring without identity. It satisfies all the other properties in the definition of a ring. So we will not be able to say that the set of even integers is a ring under the definition I've given. We can also define left and right identities in situations where there is no multiplicative identity. Actually, you can make the definition when there is, but there's not any point to it. I'll explain that in a minute. Let R be a ring either with or without multiplicative identity. An element 1 sub R is a right identity if A times 1 sub R equals A for all elements A in the ring, and similarly left identities defined this way. An element that is both a left and a right identity, in other words, what we are just calling an identity, is often called a two-sided identity or simply an identity. But for us, since we're requiring an identity, I'm going to leave it to you to show that our multiplicative identity is the only one-sided identity in the ring. Example, let M be the family of all 2 by 2 real matrices of the form AABB. So in the first row, the entries are the same in both columns. Also in the second row, the entries are the same in both columns. And we use the usual addition and multiplication of matrices. This is an abelian group with an associative product that satisfies the distributive laws. So it is in fact a non-commutative ring without identity. And I'll leave that for you to show. Now, the matrix equation given here, AABB times XXYY equals AABB, this will hold for all A and B, in other words, for all matrices AABB, if and only if X plus Y equals 1. So this ring, in fact, has infinitely many right identities, because there are infinitely many solutions to this equation. However, if you reverse the order here, then this has no solutions for all A and B. There's not a single XY pair that satisfies this equation for all A and B. So there is no left identity whatsoever. So here we have a ring without identity that has infinitely many right identities but no left identity. This is an example of the, let's say, strange behavior that can occur with a weak form of multiplication, and also in this case with no identity. One of the key features of rings is that non-zero elements need not, and very often do not, have multiplicative inverses. And those elements that do have an inverse then have a special name. An element A in a ring R is a unit, or is said to be invertible if it has a multiplicative inverse. And that would be an element B for which AB equals 1 and BA equals 1. We need both of these because we didn't say this is a commutative ring. B is referred to as the multiplicative inverse, or simply the inverse of A. And the set of all units, all invertible elements of R, is denoted by R star. If an element has an inverse, that inverse will be unique. I'll leave that for you to prove. And so if A is an R is a unit, then we can use this familiar notation A inverse for the unique inverse of A. And again, in a situation with non-commutative rings, we can also define one-sided inverses. So a left, so if A is an element of R, then, well, a right inverse of A is an element A sub R that satisfies this equation, a left inverse will satisfy this equation. These are one-sided inverses, and so for emphasis, when an element has an inverse, we could refer to it as a two-sided inverse. And as with units, as with the identity, if an element is invertible, that inverse is the only left or right inverse for the element. Another example, let M be the set of all infinite real matrices. And so it looks like this. There are infinitely many rows and infinitely many columns. We can certainly define addition of two such matrices. We just add component-wise, element-wise. So it looks like this. And this will make M into an additive group. So it's an abelian group under addition. On the other hand, multiplication's a different matter. The usual product of matrices will not extend to infinite matrices because it will produce infinite sums and they may not converge. But if we restrict the carrier set to the subset M0 of M consisting of all infinite real matrices that have only a finite number of non-zero entries in each column, then we can use the usual multiplication because the sums that are involved will only have a finite number of non-zero terms. In this case, M0 is a ring under addition and multiplication of matrices. Also, this matrix, which I call I infinity, with ones on the main diagonal and zeros elsewhere, is a two-sided identity. Now consider these two matrices. A is a matrix with ones on the superdiagonal, zeros everywhere else, and B has ones on the subdiagonal, zeros everywhere else. And of course these are in M0. And I'll leave it to you to show that AB is the identity. This is AB is the identity. On the other hand, if X is any element of M0, then this product XA, its first column, is formed by taking the dot product of the rows of X with the first column of A, but the first column of A is all zeros. So XA, no matter what X is, XA will have its first column all zeros. It cannot be the identity. So A has right inverse B, but no left inverse. I need to make some more remarks about associativity of multiplication. Some very advanced treatments of ring theory, not beginning treatments by any means, allow the possibility that multiplication is not even associative. So all you have is a binary operation that satisfies distributive law. These are called non-associative rings, and they are very complicated, well beyond the scope of this book. In fact, they are beyond the scope, I believe, in general, of any graduate course, traditional graduate course in abstract algebra, or maybe even ring theory. It's something you would study if you went to graduate school, finished your first 2 years, wanted to be a ring theorist, or an algebraist perhaps of other types. you might study non-associative rings, but it's quite an advanced topic. You've already begun to see how life can be more complicated in the absence of either commutativity or identity. You can only imagine what happens when you don't have associativity. In fact, it's rather difficult just to find a binary operation, a useful one that's non-associative. There is one, and that is the cross product of vectors in R3. That's non-associative. In any case, the examples in our discussion make it clear that whenever you see the term ring in the literature, you need to make sure that you understand what the author means by that term. Is multiplication associative? The answer to that is probably yes. Is there an identity? That could be, maybe not. Have to check what the author's definition is. Same thing for commutativity. That's unprecedented because vector spaces have a single definition. Groups are much more carefully set up. There's either commutative group or non-commutative group, and that's all you have to worry about. Fields also, there's one definition. But for rings, there are three definitions. Ring with identity, ring with or without identity, commutative ring, and non-associative. So there's 4 possible definitions. Here's some notation you would expect, I think. If you want to add A and the additive inverse of B, you can write that as A minus B and call this subtraction. You can take the sum of subsets of a ring. It looks like this. Actually, I guess I should have added product as well. You can take the product xy, and that's the set of all products, little x, little y. X in capital X, Y in capital Y. You can see from my handwriting now why I don't write things out very often anymore. I used to have quite nice handwriting, but that was many years ago. You can take integer multiples of an element of a ring, and you can take integer products or exponents. And these are as you would expect. Okay, it's time we looked at examples of rings, although we've seen a few already. The set, singleton set 0 is a ring. Addition and multiplication are defined the only way they possibly could be defined. This is called the 0 ring. Notice that in this case, the additive and multiplicative identities are the same. Both of them are 0. So 0 equals 1. And in fact, I'll let you prove that if R is a ring for which 0 equals 1, then R has to be the 0 ring. Actually, I think I proved it, but you should do it yourself. The set of integers is a commutative ring under the usual operations, as is the rational numbers, the real numbers, the complex numbers. The only units in Z are positive and negative 1. The set Zn that we are quite familiar with in our study of group theory is a commutative ring under addition and multiplication modulo n. We already know it's an abelian group. We studied that in the group theory course. These are the two operations. One is the identity, the multiplicative identity. And I'll use this symbol with the 3 lines, which is common sub n for congruence mod n, when I need to emphasize the n. So that's the definition here. And as I mentioned in the group theory course, this notation, Z mod NZ, is preferred over Zn by many mathematicians because when n is a prime, p, Zp is also used for the p-adic integers. But we're not discussing the p-adic integers in this book, in this course, and I prefer the simpler notation that I grew up with. The set of real or complex n by n matrices is a non-commutative ring, at least for n bigger than or equal to 2, under matrix addition and multiplication. We'll call these matrix rings. We've discussed them at length in the linear algebra course. And this generalizes to matrices over any field. I had some printer problems here, so there's some ink spots. I hope it's not going to be too bad. Okay. The set R square bracket x of all real polynomials in a single variable. X is a commutative ring under the usual operations of polynomial addition and multiplication. And we can extend that to the polynomials in n variables. Also, the base field R here can be replaced by C, or in fact any field. This is kind of a prototype of rings, the integers and the polynomial rings and the matrix rings. If X is a non-empty set and F is a field, then the family F square bracket X of all polynomials over the field F with variables from the set X. And this differs from the previous one because X could be an infinite set. So there would be infinitely many variables. This is a ring under the usual addition and multiplication of polynomials. When X is an infinite set, you have infinitely many variables. Each polynomial can involve only a finite number of variables. So here's an example. Next example, let R be a commutative ring. This is R double square bracket X. I don't know that this is standard notation, but it seemed reasonable. This set of all formal power series in X over the ring. So the objects look like this. This is a ring under formal addition and multiplication, again using the usual rules of algebra. If R is a ring and X is any non-empty set, this notation, and we've seen this before, is the set of all functions from X to R. As long as R is a ring, X need not have any algebraic structure. This set is a ring under addition and multiplication of functions. If R is a ring, then this set of functions on R, from R to R, is a non-commutative ring in general under addition and, this time, composition of functions. If F is a field, then the set of all sequences, infinite sequences, with members from F, is a ring under the component-wise operations. You add component-wise, you multiply component-wise. And in connection with this ring, we can define these two functions that we used in previous courses. The right shift function, rho, shifts the members of the sequence over one place to the right and puts a 0 in the first position. Left shift deletes the first member, moves all the others one position to the left. The family CAB of real continuous functions on the interval AB is a commutative ring with identity under addition and multiplication of functions. Here's a more interesting example you probably haven't seen before, you may not have seen before. Consider the family C0 of functions, each of which is defined and continuous on some open interval of the real line containing 0. So an interval, open interval about 0. Now different members of C0 can be defined and continuous on different open intervals about 0. I should emphasize that these are real functions. We can define a binary operation on C0. F is related to G if F and G agree on some open interval about 0. This is easily seen to be an equivalence relation, and not to be too clinical, its equivalence classes are called germs of continuous functions at 0. The family of germs can be added and multiplied. You can pick any representative of the equivalence classes, add them, multiply them. And so this you have to check that this is well defined, which I've done here, and it's something you should do before reading this. The family then G0 of germs of continuous functions at 0 actually forms a commutative ring under addition and multiplication of functions. And we'll have more to say about germs in due course. Here's an example that shows a connection between different branches of algebra. Let A be an additive abelian group. And you might recall that a group homomorphism sigma from A to A, so the domain and codomain are the same, these are called group endomorphisms. And we'll let end A be the family of all group endomorphisms of A. We can define addition of group endomorphisms element-wise, and we get an abelian group. Composition is well defined, and it's associative. The left distributive law holds, and that is here. I'll leave that for you to prove without looking. You can also prove the right distributive law holds. The identity function is the multiplicative identity, and so end A is actually a ring under these operations. And I'll let you think about commutativity. So from a simple little abelian group A, we get a ring end A. Finally, as a final example, it's a little different from what we've seen so far and shows the diversity of the notion of a ring. Suppose X is a non-empty set, and let R be the power set of X, which is, as you know, the family of all subsets of X. We can define multiplication in R as intersection, and addition as symmetric difference. And I'll leave it to you to show that this is a commutative ring with identity. Let's talk further now about the units in a ring. The set R star of all units in a ring R is a group under multiplication called the group of units. of R. R star, I think, is a fairly standard notation for the group of units. And I'm going to leave this for you to prove. In the matrix ring Mn of R, it's well known, of course, that a matrix A is a unit if and only if its determinant is non-zero. In the ring R square bracket X of real polynomials, the units are the non-zero constant polynomials. In other words, the non-zero real numbers. If R is a commutative ring, and R double square bracket X is the ring of formal power series in X over R, then the units of this ring are the formal power series that have unit constant coefficients. So R double square bracket X star is the set of all power series f of X, of which f of 0, which is the constant term, is in R star. And to see this, note that if we have a power series, it's a unit if and only if there exists another power series for which this product is 1. Now, if this equation holds, then comparing constant terms, we get A naught B naught equals 1. And so both A naught and B naught are units. And A naught in particular is invertible with inverse B naught. Conversely, if A naught is a unit, then B naught would be uniquely determined by this equation as A naught inverse. And once B naught through Bn minus 1 have been uniquely determined by this equation, then we can solve for Bn. First we equate coefficients of x to the n. We get this equation. Push everything to the other side except A naught Bn, and then because A naught is invertible, we can multiply both sides by A naught inverse and get a unique value for B sub n. And so this shows that a power series has an inverse if and only if its constant term has an inverse. I've given an alternative proof here, and I'm going to let you read this for yourself. The units of the ring Zn are the elements of Zn that are relatively prime to n. So that looks like this in symbols. And this follows from the fact that the following statements are equivalent. An element R in Zn and n are relatively prime. Greatest common divisor is 1. Equivalent to there are integers a and b for which AR plus Bn equals 1, or in other words, that is for which AR is congruent to 1 mod n. This follows from Bezos' identity, something we used quite often in the previous lecture series. That's equivalent to saying that in Zn, AR is actually equal to 1. And that's equivalent to saying that R is a unit in Zn with inverse equal to A. Here's an example that you might not have seen before that will come up several times in the sequel. Let Z square bracket I be the set Z plus Zi. In other words, all of the complex numbers where the real and imaginary parts are integers. I squared is -1, it's the usual imaginary number. Okay. So this is a subset of the complex numbers. This is a commutative ring under addition and multiplication of complex numbers. It's called the ring of Gaussian integers. Let's check the units. To do so, we define something that's very useful in studying the Gaussian integers. It's called the Gaussian Norm. I'll use capital N, maps the Gaussian integers to the integers, and all it is the square of the usual complex norm. So it's a squared plus b squared. This function is very useful in studying the Gaussian integers, due in large part to the fact that it's multiplicative. So if alpha and beta are Gaussian integers, the norm of the product is the product of the norms. And that comes in very handy. Now, if alpha equals a plus bi is a unit, then there's another Gaussian integer for which this product is 1, and we take the Gaussian norm and use the multiplicativity, and we get a squared plus b squared, that's the norm of alpha, times x squared plus y squared, which is the norm of beta, equals 1. These guys are integers, and so each of these factors has to be 1. These are positive integers. Okay. So each norm is 1, but the norm of Gaussian integer is 1 if and only if the integer is plus or minus 1 or plus or minus I. So the units must be among these 4 Gaussian integers, but each of these is a unit, so this is in fact the group of units, plus or minus 1, plus or minus I. So you see in this case that the Gaussian norm made it very easy to determine the units. So I might suggest you see if you can figure out what the units are without using the Gaussian norm. See how that goes. In this polynomial ring f square bracket x, where f is a field, the only units are the non-zero constant polynomials. But that's not the case for polynomial rings over a ring r square bracket x. The coefficients now come from a ring. Here's an example. We use as the base m2 of z. These are the 2 by 2 matrices with integer entries. This polynomial, which is linear, has an inverse, and I'll leave it for you to figure out what it is. Returning to the germs, a germ, square bracket f, is a unit if and only if f of 0 is non-zero. And to see this, we have this product of germs equals the identity germ, implies these two germs are equal, which implies fg is equivalent to 1. And that means that the two agree on some open interval around the origin. And so they agree at the origin, which means this must equal 1, this product. And so f of 0 is non-zero. Conversely, if f of 0 is non-zero, then since f is continuous, there's an open interval I about 0 in which f is non-zero. And so we can define g of x to be 1 over f of x in that interval, and then that will give us the inverse. Square bracket f, this germ, its inverse is the germ containing g. Speaking about units and non-units, Let's answer some questions that, frankly, I haven't seen in other books. It must be in there somewhere, but anyway. If R is a ring, then the set R star of units is closed under multiplication. I asked you to prove that earlier. So the product of two units is a unit. It's not difficult to prove. This raises, well, three additional questions. What about the product of a unit and a non-unit? What about the product of two non-units? Also, if a product is a unit, do the factors, at least one of them anyway, have to be units? Well, as far as this third question, if AB is equal to U, and U is a unit, then U inverse AB is 1, and so B is left invertible. Also, if AB equals U, we can write A quantity BU inverse equals 1. And so A now is right invertible. So B's left invertible, A is right invertible. That's not quite what we were hoping. But if R is commutative, then A and B both of them are invertible. So if R is a commutative ring, the product of unit, and if the product of elements is a unit, both of the factors must be units. But if R is non-commutative, life is, as usual, more complicated. And here's an example. For the ring of real sequences, consider the non-commutative ring R of all functions on this sequence ring. Functions from sequences to sequences with the usual sum and composition of functions. Then the units of R will be the bijective functions. These are the functions that have inverses under composition. For the left shift function lambda and the right shift function rho, we have lambda rho equals the identity. If you first do a right shift, you don't lose anything. You stick a 0 in front. Then you do the left shift, you simply remove the 0. So you haven't done anything. So lambda rho is a unit. It's the identity, in fact. However, rho is not surjective, the right shift, because you always have a 0 in the first position. And lambda is not injective, so neither rho nor lambda is a unit. So the product is a unit, the composition, but neither factor is a unit. So we can't improve upon this right and left invertibility business here in general. And I'm going to leave it for you to fill in the rest of this theorem, the answer to the other question. The product of two units is a unit. I've already asked you to do that. The third one is what we just discussed. And the second one, the product of a unit and a non-unit is a non-unit. I'll leave that for you as well. These, you don't really need to memorize. They should make sense. And you should be able to produce, at least for 1 and 2, you should be able to produce a one-line proof very quickly. For part 3, I suppose it's what you would expect is if the product is a unit, the factors are units. So you can say to yourself, well, for a commutative ring, it's what I expect, but not for a non-commutative ring. How about sums? What about the sum of units and non-units? Well, here anything goes. And if you're as old as I am, you might recognize that as the title of a song from Cole Porter. The sum of two units may or may not be a unit. The sum of two non-units may or may not be a unit. The sum of a unit and a non-unit may or may not be a unit. That's what we mean by anything goes. That we can't say anything about the sums. And so what we need here are examples. And they all come from Zn. In Z7, for example, 1 plus 2 equals 3. 1 is a unit, 2 is a unit, 3 is a unit, because they're all relatively prime to 7. 3 plus 4 is 0, however. 3 and 4 are relatively prime to 7. They're units. 0 is a non-unit. And I would suggest that you see if you can do the other two in Z6. And I'll leave it for you to think about that. Now, despite the rather disappointing previous theorem, I suppose it cuts both ways. It's disappointing in that you can't say anything, but it's slightly non-disappointing in the fact that you don't have to remember anything, right? Nothing works. But we'll see in a later chapter that it's not terribly hard to characterize rings in which the sum of non-units is a non-unit. So that's something. These are actually called local rings, but not for that reason, for an entirely different reason.